In the middle of the 19th century, physics was a science filled with confidence and confusion at the same time. Confidence came from remarkable successes. Newton's laws still ruled motion, thermodynamics was rapidly maturing, and electricity had begun to move from the laboratory into everyday life through telegraphs and early electrical devices. Confusion, however, lay beneath the surface, especially in the understanding of electricity and magnetism. These two phenomena were clearly related, yet no one could say with certainty how deep that relationship truly was. Scientists sensed that a unifying principle existed, but experimental proof lagged behind theoretical speculation. This tension formed the scientific atmosphere into which Henry Rowland's work would later emerge. Electricity, as understood at the time, was primarily a study of charges at rest and charges in motion through conductors. Static electricity had been known since antiquity, observed in amber attracting bits of straw when rubbed. By the 18th century, scientists like Coulomb had quantified electric forces, showing that electric charges exert forces on one another according to precise mathematical laws. Electricity could be stored in Leyden jars, released in sparks, and measured with increasing accuracy. Yet these phenomena were often treated as isolated curiosities rather than pieces of a unified framework. Magnetism, on the other hand, seemed almost mystical. Lodestones had been known for centuries to attract iron and influence compass needles. Earth itself acted like a giant magnet, guiding navigation across oceans. Magnetic effects appeared permanent and directional, unlike the fleeting nature of static electricity. For a long time, magnetism was considered a unique force of nature, unrelated to electricity except in the most superficial ways. Even as experimental techniques improved, magnetism retained an aura of mystery. The first major crack in the wall separating electricity and magnetism came in 1820, when Hans Christian Ørsted discovered that an electric current could deflect a magnetic compass needle. This observation stunned the scientific community. For the first time, electricity was seen to produce a magnetic effect directly. The implication was clear: the two phenomena were not independent. However, the nature of the connection remained ambiguous. Did electricity generate magnetism only under special circumstances, or was magnetism simply another face of electricity itself? Following Ørsted's discovery, André Ampère developed a mathematical description of the magnetic forces between current-carrying wires. His work showed that currents exert forces on one another in ways strikingly similar to the forces between magnets. Ampère even proposed that magnetism in materials might arise from tiny circulating currents within atoms. This idea was bold and imaginative, but it lacked direct experimental confirmation. Atomic structure itself was poorly understood, and electrons had not yet been discovered. As a result, Ampère's hypothesis remained speculative. Meanwhile, Michael Faraday transformed the study of electromagnetism through his experimental genius. Faraday demonstrated electromagnetic induction, showing that changing magnetic fields could produce electric currents. He introduced the revolutionary concept of fields, invisible entities filling space and transmitting forces without direct contact. Faraday's ideas challenged the dominant Newtonian notion of action at a distance and hinted at a deeper unity between electricity and magnetism. Yet Faraday, brilliant as he was, struggled to express his ideas mathematically, which limited their immediate acceptance among theoreticians. James Clerk Maxwell later provided the mathematical language Faraday's insights demanded. Maxwell's equations unified electricity and magnetism into a single theoretical framework, predicting that electric and magnetic fields propagate together as electromagnetic waves traveling at the speed of light. This theoretical triumph suggested that light itself was an electromagnetic phenomenon, an idea confirmed experimentally soon afterward. Despite this success, Maxwell's theory raised new questions rather than closing the book on electromagnetism. One of the most pressing questions concerned the true origin of magnetic fields. According to Maxwell's equations, magnetic fields are generated by electric currents and changing electric fields. But what exactly is an electric current? In practical terms, it was defined as the flow of electricity through a conductor. Yet this definition subtly avoided a deeper issue. Was magnetism caused by the flow of charge itself, or did it depend on the presence of a conducting medium, such as a metal wire? This distinction may seem subtle, but it was crucial. If magnetism depended on currents in wires, then magnetism might be a secondary effect tied to specific materials and circuit configurations. If, however, magnetism arose from the motion of electric charge alone, regardless of how that motion occurred, then magnetism would be a fundamental consequence of electricity. This would mean that any moving charge, even one carried mechanically through space, should generate a magnetic field. At the time, this idea remained untested. Most experiments involved currents in wires, where charges moved through conductors in closed loops. The wire itself could not be separated from the phenomenon. Critics argued that magnetism might result from interactions between electricity and the material properties of conductors. Perhaps the lattice of atoms in a wire played an essential role, or perhaps magnetism arose from subtle chemical or mechanical effects within the metal. Without an experiment that isolated charge motion from conduction, the debate could not be resolved. Adding to the uncertainty was the limited understanding of electric charge carriers. Electrons had not yet been identified, and the microscopic picture of electricity was incomplete. Electricity was often treated as a continuous fluid rather than a collection of discrete particles. In such a framework, it was difficult to imagine charge moving independently of matter. As a result, many physicists hesitated to accept the idea that pure charge motion, detached from a conductor, could produce magnetism. There was also a philosophical dimension to the problem. Physics in the 19th century was deeply influenced by mechanistic thinking. Forces were often explained in terms of physical contact, stresses in hypothetical media, or motions of invisible substances. Magnetism, in particular, was sometimes attributed to swirling vortices in an all-pervading ether. In this context, the notion that magnetism could arise simply because charge was moving challenged deeply held assumptions about causation and physical reality. Experimental limitations further complicated the situation. Any magnetic effect produced by moving charges without a wire was expected to be extremely weak. Detecting such an effect required instruments of extraordinary sensitivity and experimental setups designed to eliminate every possible source of interference. Many physicists doubted whether such an experiment was even feasible with the technology of the time. Despite these challenges, the question refused to fade away. The growing success of Maxwell's theory demanded experimental validation at every possible level. If moving charge truly generated magnetism, then this principle should hold universally, not just in special cases involving wires and circuits. The absence of direct evidence became increasingly uncomfortable for a scientific community that valued empirical confirmation. This intellectual tension created a fertile environment for innovation. Physicists were increasingly willing to challenge assumptions and design experiments that pushed the limits of precision. The rise of laboratory-based physics, particularly in Europe and the United States, emphasized careful measurement and reproducibility. Instruments such as sensitive galvanometers and magnetic needles allowed researchers to detect effects that would have been invisible only decades earlier. It was within this context that Henry Rowland began to think deeply about the relationship between electricity and magnetism. He was not merely interested in confirming existing theories, but in clarifying their physical meaning. The question driving his work was deceptively simple. If electric charge is set into motion by mechanical means, without forming a current in a wire, will it produce a magnetic field? This question cut to the heart of the scientific uncertainty of the era. An affirmative answer would demonstrate that magnetism is an inevitable consequence of moving charge, independent of materials or circuits. A negative answer would suggest that magnetism depends on something more than charge motion alone, perhaps involving the structure of conductors or the properties of matter itself. The importance of resolving this issue cannot be overstated. The unification of electricity and magnetism was not merely an abstract theoretical goal. It had practical implications for emerging technologies and for the broader understanding of nature. A clear answer would shape how future generations thought about forces, fields, and the fundamental constituents of matter. Thus, before Rowland ever set up his apparatus or observed a magnetic needle deflect, the scientific stage was already set by decades of discovery, debate, and uncertainty. Electricity and magnetism stood tantalizingly close to full unification, yet separated by a gap that only a carefully designed experiment could bridge. The mystery was not whether electricity and magnetism were related, but how deep that relationship truly went. It was this unresolved question, born of both theoretical ambition and experimental frustration, that demanded an answer and ultimately led to one of the most elegant demonstrations in the history of electromagnetism. As the 19th century progressed, the unresolved questions surrounding electricity and magnetism began to feel increasingly urgent. Scientific knowledge was expanding rapidly, yet the foundations of electromagnetism still rested on assumptions that were not fully tested. Theoretical unity had been proposed, mathematical elegance had been achieved, but the physical interpretation of these ideas remained incomplete. Many physicists were uneasy with a situation in which equations seemed to know more about nature than experiments could clearly demonstrate. One major source of discomfort lay in the reliance on conductors as the setting for nearly all electromagnetic experiments. Wires, coils, and circuits dominated laboratories. Whenever magnetism appeared, it was always alongside a current flowing through metal. This raised an unavoidable question. Was the metal merely a passive pathway for electric charge, or was it actively involved in generating magnetic effects? If magnetism depended on properties of matter rather than on charge motion itself, then the theoretical unification of electricity and magnetism would be fundamentally flawed. This concern was not trivial. At the time, matter was often thought to play a central role in transmitting forces. The hypothetical ether, for example, was widely believed to be the medium through which light and electromagnetic effects propagated. If magnetism required a material medium, then moving charges in empty space might behave very differently from charges in a conductor. Such a possibility would limit the universality of electromagnetic theory and complicate its application to nature as a whole. Another layer of uncertainty came from the concept of electric current itself. A current was defined operationally, measured by its effects: heating a wire, deflecting a needle, producing chemical reactions. But what was actually moving? Without a clear understanding of charge carriers, the idea of current was abstract. Some physicists imagined electricity as a fluid flowing through matter, others as a vibration or stress transmitted through an ether. In such a conceptual landscape, the statement "moving charge creates magnetism" was far from obvious. The difficulty was compounded by the fact that magnetism often appeared steady and permanent, while electricity seemed transient and controllable. Permanent magnets retained their properties without any visible motion, while electric charges at rest produced no magnetic effects at all. This asymmetry puzzled researchers. If magnetism truly arose from moving charge, why did magnets not appear to involve motion? This apparent contradiction hinted at processes occurring at scales far smaller than could be observed, but without experimental confirmation, such ideas remained speculative. At the same time, experimental physics was undergoing a transformation. Precision measurement was becoming a defining feature of serious scientific work. Physicists increasingly believed that even the most subtle effects could, in principle, be detected if experiments were designed carefully enough. This growing confidence in experimental technique encouraged researchers to revisit questions that had previously been dismissed as impractical. The challenge was to design an experiment that separated charge motion from electric current in a conductor. Such an experiment would need to move electric charge through space mechanically, without allowing it to flow through a wire. The expected magnetic effect would be extraordinarily weak, easily masked by Earth's magnetic field or by stray electrical influences. Detecting it would require not only sensitive instruments, but also exceptional control over experimental conditions. Despite these difficulties, the intellectual pressure to resolve the issue continued to build. Maxwell's equations had achieved remarkable predictive success, yet critics pointed out that mathematical consistency was not a substitute for empirical proof. A theory claiming universal validity had to be tested in as many distinct physical situations as possible. The absence of a direct demonstration that pure charge motion produced magnetism was an obvious gap. This gap was especially significant because it touched on the very meaning of magnetism. If magnetism were simply electricity in motion, then magnetic forces would not be fundamental in their own right, but emergent from electric phenomena. This would reshape how physicists classified forces and understood interactions at a basic level. It would also influence how future theories, including those dealing with atomic and subatomic processes, were constructed. There was also a broader philosophical implication. The 19th century witnessed a gradual shift away from viewing nature as governed by separate, independent forces toward seeing it as structured by unifying principles. The unification of electricity, magnetism, and light was one of the great triumphs of this approach. Yet unification without experimental grounding risked becoming a purely intellectual exercise. Demonstrating that moving charge alone could generate magnetism would anchor this unification firmly in observable reality. As debates continued, some physicists attempted indirect arguments. They reasoned that since currents produced magnetism and currents involved moving electricity, motion must be the essential ingredient. Others countered that the structure of the conductor might play a crucial role, perhaps guiding or organizing the electricity in a way necessary for magnetic effects. Without an experiment that eliminated the conductor entirely, these arguments remained unresolved. The absence of such an experiment also limited the interpretation of magnetic materials. If magnetism arose from microscopic currents, as Ampere suggested, then those currents must consist of moving charges confined within atoms. But atoms themselves were poorly understood, and the idea of internal charge motion was speculative. Experimental confirmation at the macroscopic level would lend credibility to these microscopic hypotheses. Meanwhile, technological developments added urgency to the problem. Electrical engineering was beginning to emerge as a practical discipline. Understanding the true nature of electromagnetic interactions promised to improve the design of generators, motors, and communication systems. A deeper grasp of how magnetism arose could lead to more efficient and reliable technologies. Within this climate of theoretical promise and experimental uncertainty, the stage was set for a decisive investigation. What was needed was not a complex theoretical argument, but a clear, unambiguous demonstration. An experiment that showed magnetism appearing solely because electric charge was moving, with no wire, no current loop, and no chemical or thermal effects, would settle the matter definitively. Such an experiment would do more than answer a narrow technical question. It would validate the conceptual leap that electricity and magnetism were not merely related but fundamentally inseparable. It would show that magnetism is not a mysterious property of certain materials or configurations, but a natural and inevitable consequence of charge in motion. This realization would ripple outward, influencing how physicists thought about fields, forces, and the structure of matter itself. Thus, by the time Henry Rowland undertook his investigation, the problem was ripe for resolution. Decades of discovery had narrowed the question to its essence, and advances in experimental technique had made its investigation feasible. The scientific community stood at a moment of anticipation, aware that a simple yet decisive experiment could clarify one of the most important relationships in physics. What remained was the courage to attempt what many believed too subtle to observe, and the patience to design an experiment capable of isolating a nearly imperceptible effect. The mystery was no longer whether electricity and magnetism were connected, but whether that connection could be demonstrated in its purest possible form. The answer to that mystery would soon transform a long-standing suspicion into an established physical principle, completing a crucial chapter in the story of electromagnetism. In the midst of the 19th century's vibrant scientific revolution, Henry Augustus Rowland emerged as a figure of remarkable precision and intellectual curiosity. Born in 148 in Honesdale, Pennsylvania, Rowland was a product of an era in which American science was beginning to assert itself on the global stage. His early life was marked by an insatiable curiosity and a methodical approach to understanding the natural world, qualities that would later define his contributions to experimental physics. Rowland's work, particularly in the domain of electricity and magnetism, would not merely add incremental knowledge, but would confront one of the most subtle and fundamental questions in physics: the relationship between moving charges and magnetic fields. By the time Rowland began his career, the landscape of electromagnetism had been shaped by several towering figures. Hans Christian Ørsted had shown that an electric current deflected a compass needle, revealing an intimate connection between electricity and magnetism. Andremer v. Ampere had mathematically described the forces between currents and hypothesized that magnetism in materials might originate from microscopic circulating currents. Michael Faraday had transformed understanding with his concept of electromagnetic induction, emphasizing the role of fields and introducing a visualization that emphasized the dynamic, interactive nature of electromagnetic phenomena. James Clerk Maxwell, building upon Faraday's ideas, had formulated a comprehensive set of equations predicting the behavior of electric and magnetic fields, even uniting them with the nature of light itself. Yet, amidst this theoretical progress, there remained an ambiguity that Rowland found compelling. While it was clear that electric currents in conductors produced magnetic effects, it was not known whether the motion of electric charge itself, independent of the conductive medium, could generate a magnetic field. Most experiments relied on wires, coils, or currents in closed circuits, where charges flowed under the guidance of conductive materials. Critics argued that magnetism could be a property emerging from interactions between charges and the conductor itself, rather than from charge motion alone. Rowland's genius lay in recognizing that this distinction was crucial, not only for the interpretation of Maxwell's theoretical framework, but for the broader understanding of electromagnetism. Rowland approached this question with a unique combination of creativity and rigor. He was not content to rely on indirect arguments or theoretical speculation. He sought empirical evidence that could decisively demonstrate whether moving charges alone could create magnetic effects. To achieve this, he needed a scenario in which electric charges could be set in motion without flowing through a conventional wire or circuit. This required both inventive experimental design and meticulous attention to sources of error, for the expected magnetic effects would be extremely weak and easily obscured by external influences. His solution was conceptually elegant. By considering a mechanically rotating body capable of carrying an electric charge, Rowland could generate motion of charges in a controlled and measurable way. The idea was deceptively simple. If a charged object rotates, the charges it carries move in a circular path, effectively producing a current. If moving charge produces magnetism, then such a rotating charged object should generate a measurable magnetic field. This approach removed the conductor from the equation, isolating the effect of charge motion itself. This idea also reflected a deep understanding of the theoretical principles at play. Maxwell's equations indicated that a current or moving charge would produce a magnetic field, but these equations were often applied in the context of conventional circuits. Rowland recognized that a rigorous test required creating a situation that tested the equations in a more fundamental setting. If a magnetic field could be detected around a rotating charged disk, it would provide strong support for the idea that magnetism arises intrinsically from the motion of charge, rather than from properties of the material carrying the current. The execution of this concept, however, posed significant challenges. Rotating a charged body was not sufficient. The experiment demanded extraordinary precision in controlling charge distribution, rotational speed, and environmental conditions. Rowland had to ensure that the charges were distributed uniformly across the rotating body, for uneven charge could produce complex effects difficult to interpret. The rotation needed to be stable and well characterized, since variations in speed or axis could introduce spurious magnetic signals. Additionally, the experiment had to be shielded from external magnetic influences, including Earth's own magnetic field, stray currents, and vibrations, all of which could overwhelm the subtle magnetic effect he sought to measure. Rowland also innovated in the instruments used for detection. The magnetic field generated by the rotating charges was expected to be minuscule, far weaker than that produced by typical electric currents in wires. Detecting it required highly sensitive magnetic needles and careful calibration. Every aspect of the experimental setup demanded scrutiny, from the placement of the detection apparatus to the method of mounting the rotating disc. Rowland's meticulous approach reflected not only his technical skill, but also a philosophical commitment. A clear, unambiguous demonstration required eliminating any possible source of doubt or alternative explanation. In designing his experiment, Rowland also drew upon the broader experimental tradition of 19th century physics. He was deeply aware of the successes and limitations of earlier work, from Ørsted's compass deflections to Faraday's induction experiments. He recognized that empirical science progresses not only through theoretical insight, but through the careful isolation and testing of specific variables. By focusing on the motion of charge itself, independent of the conductor, he was able to target the precise question that remained unresolved. This approach exemplified a shift in physics toward increasingly controlled, quantitative, and conceptually clear experiments, reflecting a maturation of the discipline. Furthermore, Rowland's question was not merely technical. It carried profound conceptual implications. If confirmed, the effect would show that magnetism is a direct manifestation of moving charge. This would validate Maxwell's theoretical framework at a fundamental level and provide a bridge between abstract equations and physical reality. It would also support Ampere's hypothesis that magnetism in materials could be explained by microscopic currents, suggesting a continuity between macroscopic and atomic phenomena. In other words, an elegant and precise experiment could simultaneously resolve a theoretical ambiguity and illuminate the microscopic foundations of matter. At the same time, Rowland's work had practical foresight. The late 19th century was witnessing the early stages of electrical engineering and technological application. Understanding the intrinsic relationship between moving charge and magnetism could inform the design of motors, generators, and electrical measurement devices. The principle that charges in motion produce magnetic fields underlies nearly every modern electromagnetic device, from electric generators to magnetic storage systems. Rowland's insight was therefore both theoretically and technologically prescient. Rowland's intellectual rigor extended to every detail of the experimental methodology. He considered potential sources of error, such as electrostatic interactions, mechanical vibrations, and magnetic contamination, and implemented measures to minimize them. He also explored variations in the experimental setup, reversing the direction of rotation and altering charge polarity, to test whether the observed effects consistently matched theoretical predictions. This thoroughness ensured that any observed magnetic deflection could be confidently attributed to the motion of charges, rather than to extraneous factors. Moreover, the experiment exemplified a profound understanding of the interplay between theory and observation. Theoretical equations suggested a phenomenon, but the world does not always conform to mathematical expectation. Rowland's approach exemplified the scientific ideal. Theory guides the experiment, but empirical evidence validates the theory. By constructing a test that isolated the effect of interest, Rowland was able to bridge the gap between abstract prediction and observable reality. Rowland's work also reflected a broader philosophical orientation in physics, the belief that nature's principles could be revealed through careful, methodical experimentation. He understood that fundamental discoveries often require ingenuity, patience, and precision. The motion of charge was an abstract concept, invisible to the eye, yet Rowland's experiment translated it into measurable magnetic effects. This capacity to render the invisible visible exemplifies the essence of experimental physics, transforming theoretical speculation into demonstrable fact. Through this meticulous approach, Rowland positioned himself to address one of the most subtle and profound questions of his time. He did not merely confirm known relationships or refine previous measurements. He sought to uncover a fundamental truth about the natural world. The motion of electric charge, he hypothesized, is inherently magnetic, a principle with implications spanning theoretical physics, material science, and technology. This ambition, combined with rigorous method, characterizes Rowland's contributions and situates his work within the lineage of transformative scientific achievement. Ultimately, Rowland's focus on the motion of electric charge exemplifies a defining moment in the maturation of electromagnetism. By isolating the variable of interest and designing a precise experiment, he addressed a question that had remained ambiguous despite decades of study. His work reflects the interplay between theoretical insight and experimental ingenuity, demonstrating how carefully posed questions can yield profound discoveries. In doing so, Rowland not only advanced the understanding of magnetism, but also set a standard for the scientific method itself, one in which clarity, precision, and conceptual insight converged to illuminate the fundamental workings of nature. As Rowland's ideas began to take shape, the practical challenges of turning theory into experiment became increasingly apparent. Generating a measurable magnetic effect from moving charges, independent of any conductor, required not only ingenuity, but also a painstaking approach to experimental design. The very concept of isolating charge motion was novel. While currents in wires had been studied extensively, removing the wire as a medium demanded rethinking the setup from first principles. Rowland realized that the charges themselves had to be distributed in a controlled manner, so that their motion could be quantified and their magnetic effect detected with confidence. Any unevenness in the charge distribution could produce ambiguous results, potentially masking the subtle phenomenon he sought to observe. The choice of apparatus was critical. Rowland envisioned a rotating disc or similar body that could carry electric charge uniformly. Mechanical rotation would simulate a current, with charges moving along a circular path. However, rotational systems introduced their own complications. Variations in rotational speed or axis could create disturbances in the magnetic field measurements, while friction and vibrations threatened to obscure the tiny effect. The meticulousness required went beyond ordinary laboratory work. It demanded not only mechanical precision, but also careful control of environmental conditions, including shielding from external magnetic fields, such as the Earth's own, and minimizing electrostatic interactions with nearby objects. Detection of the magnetic effect presented a further challenge. The anticipated field produced by the rotating charges was orders of magnitude weaker than those produced by conventional currents in wires. To detect it, Rowland relied on sensitive magnetic needles and careful calibration procedures. The needles had to be isolated from any extraneous influences and positioned to respond only to the magnetic field generated by the moving charges. Even minor disturbances, air currents, vibrations, temperature changes could alter the readings. Every component of the setup required meticulous design, reflecting Rowland's characteristic attention to experimental detail. Rowland also understood the importance of variation and repetition. A single measurement would not suffice. Confirmation demanded multiple trials under varying conditions. By reversing the direction of rotation, changing the sign of the charge, and carefully observing the response of the magnetic needle each time, Rowland could demonstrate that the observed effects were consistent with the theoretical expectation that moving charges produce magnetism. This systematic approach ensured that alternative explanations, such as accidental magnetic contamination or mechanical disturbances, could be ruled out with confidence. The conceptual clarity of the experiment matched its technical rigor. Rowland's design isolated the essential variable, the motion of charge, while minimizing confounding factors. In doing so, he addressed the central ambiguity in electromagnetism: whether magnetism is a fundamental consequence of moving charges or a secondary effect arising from interactions with a conductor. By removing the wire from the experiment, Rowland directly tested the theoretical principle underlying Maxwell's equations. This step was critical, for it moved the understanding of magnetism from indirect inference to direct empirical demonstration. Rowland's approach also reflected a broader scientific philosophy. He recognized that deep physical principles often manifest subtly, and that careful, controlled observation is essential to uncovering them. Rather than relying on dramatic effects or large currents, he designed an experiment that made the invisible visible, translating an abstract theoretical idea into a measurable physical phenomenon. In this way, the work exemplifies the ideal of 19th-century experimental physics: precision, creativity, and conceptual insight combined to produce clarity about the natural world. Moreover, the implications of Rowland's experimental focus were far-reaching, demonstrating that magnetism arises directly from the motion of electric charge, provided a firm foundation for later theoretical and technological developments. It offered empirical support for the hypothesis that magnetic properties of materials could be explained by microscopic currents, a concept that would later gain clarity with the discovery of the electron. It also reinforced the notion of a unified electromagnetic field, strengthening the bridge between abstract theory and observable reality. In addition to its theoretical importance, Rowland's work had practical resonance. The principle that moving charges generate magnetic fields underpins modern electrical engineering, from the design of motors and generators to magnetic storage and imaging technologies. Rowland's experiment, by isolating the fundamental cause of magnetism, laid the groundwork for understanding and harnessing electromagnetic phenomena in countless applications. His work illustrates how foundational research, driven by curiosity and precision, can have enduring technological impact. The experiment also highlighted the interplay between theory and practice. Maxwell's equations predicted the relationship between moving charge and magnetism, but observation was necessary to confirm the prediction. Rowland's meticulous approach exemplified the scientific ideal, using experiment to validate theory while simultaneously refining conceptual understanding. By demonstrating the magnetic effect of mechanically moving charges, Rowland not only confirmed a theoretical expectation, but also clarified the conditions under which the effect occurs, adding depth to the emerging understanding of electromagnetism. Rowland's investigation, therefore, was both a conceptual and technical triumph. It required ingenuity in experimental design, precision in execution, and patience in observation. By focusing on the motion of charge itself, he addressed a subtle ambiguity in electromagnetic theory, providing a clear empirical demonstration of a fundamental principle. This achievement reflects the essence of scientific discovery: asking the right question, designing a controlled test, and carefully interpreting the results. Furthermore, Rowland's work illustrates the broader trajectory of physics in the 19th century, moving from observation and description toward controlled, quantitative experiments that test specific theoretical predictions. The shift represents a maturation of the discipline, emphasizing the importance of precision, reproducibility, and conceptual clarity. Rowland's focus on moving charges independent of a conductor, embodies this approach, transforming a theoretical question into a tangible, measurable phenomenon. Ultimately, Rowland's attention to the question of moving charges and magnetism exemplifies the qualities of an exceptional scientist: curiosity, rigor, and insight. He recognized a gap in understanding, conceived an elegant method to address it, and executed the experiment with extraordinary care. In doing so, he not only provided a crucial empirical foundation for the theory of electromagnetism, but also demonstrated the power of thoughtful experimental design to resolve fundamental questions about nature. His work stands as a testament to the precision, creativity, and conceptual depth that define the best traditions of physics. Henry Rowland's approach to investigating the connection between moving electric charges and magnetism was marked by both conceptual elegance and experimental ingenuity. To address the fundamental question whether the motion of electric charge alone could generate a magnetic field, he devised a method that would isolate the variable of interest while minimizing confounding factors. At the heart of this approach was the design of a rotating disk capable of carrying a uniform electric charge, a device that would simulate a current without the need for a conducting wire. This experimental setup represented a critical step forward, allowing Rowland to translate theoretical predictions into observable phenomena. The choice of a rotating disk was not arbitrary. Rowland understood that if electric charges move along a circular path, they effectively constitute a current loop, and according to emerging electromagnetic theory, such a current should produce a magnetic field perpendicular to the plane of motion. By mechanically rotating a charged body, Rowland could control both the speed and direction of charge motion, thereby creating a precisely defined and measurable magnetic effect. This approach elegantly separated the motion of charges from any potential influence of conductive materials, addressing a key ambiguity in earlier experiments. Constructing such a disk required careful consideration of materials and charge distribution. Rowland needed a surface that could hold an electric charge uniformly without leakage, which meant selecting insulating materials and designing coatings that maintained a stable surface charge. Any irregularity in charge distribution could result in complex or misleading magnetic effects, undermining the experiment's purpose. By ensuring that the charge remained evenly spread across the disk, Rowland could create a scenario in which the movement of charges could be predicted and analyzed with precision. Equally important was the mechanical design of the rotation system. The disk had to spin smoothly and steadily, with minimal friction and vibration. Variations in rotational speed or axis alignment could introduce errors in magnetic measurements, so Rowland paid careful attention to the stability and balance of the apparatus. He devised methods to mount the disk on an axis that allowed free rotation while reducing mechanical disturbances. This level of engineering precision was necessary because the magnetic field generated by the moving charges was extremely weak, and any extraneous motion could easily overshadow the subtle effect he sought to observe. To detect the magnetic field, Rowland employed sensitive magnetic needles placed in proximity to the rotating disk. The needles had to be carefully isolated from external magnetic influences, including Earth's magnetic field, nearby metallic objects, and stray currents. He arranged the setup so that the magnetic needle's deflection could be attributed solely to the motion of charges on the disk. The combination of a stable rotating system and sensitive detection instruments allowed Rowland to measure a phenomenon that would have been imperceptible with less careful design. Another crucial element of the experimental design was the ability to vary conditions systematically. Rowland reversed the direction of rotation, changed the polarity of the charge, and repeated measurements multiple times to ensure consistency and eliminate sources of error. Each variation produced predictable changes in the magnetic needle's deflection, confirming that the observed effect was a direct consequence of the charge motion rather than an artifact of apparatus. This systematic approach reflects Rowland's deep understanding of the principles of controlled experimentation, isolating variables, repeating trials, and observing consistent, reproducible results. The design also anticipated theoretical implications. Maxwell's equations suggested that a moving charge generates a magnetic field, but previous experiments had relied on currents in wires. By using a mechanically rotated charged disk, Rowland created a test that extended the theoretical prediction to a more general situation. The setup was designed to demonstrate unequivocally that magnetism arises from motion itself, independent of the conductor. In doing so, the experiment provided a bridge between abstract theory and tangible observation, allowing a subtle principle of electromagnetism to be visualized and measured. Rowland's design exemplified the combination of scientific insight and practical skill. He understood the theory well enough to know which variable needed isolation and the magnitude of the expected effect, yet he also recognized the importance of mechanical and electrical precision. Every component, from the choice of materials to the sensitivity of detection instruments, was designed to ensure that the motion of charge could be studied cleanly and unambiguously. The result was an experiment that was conceptually simple but technically sophisticated, capable of revealing one of the fundamental truths of electromagnetism. In conclusion, the design of Rowland's rotating charged disk was a landmark in experimental physics. By creating a method to observe the magnetic effects of moving charge without the interference of a conductor, he was able to translate theoretical predictions into measurable reality. The setup's precision, adaptability, and conceptual clarity not only addressed a critical question in electromagnetism, but also set a standard for future experimental design. It exemplified the power of thoughtful engineering combined with theoretical insight, demonstrating that even the most subtle phenomena can be revealed through careful, systematic experimentation. Rowland's work provided a direct and elegant demonstration of the principle that moving electric charges generate magnetic fields, a cornerstone of modern electromagnetic theory. When Henry Rowland carried out his rotating disk experiment, the results he observed were subtle yet profoundly significant. The fundamental question he sought to answer was whether the mere motion of electric charge, independent of any conductor or circuit, could generate a magnetic field. By designing a system in which a uniformly charged disk rotated, Rowland had created a situation in which the charges moved in a predictable and measurable way. Observing the magnetic effects of this motion required not only precision instruments but also careful interpretation, as the expected magnetic field was extraordinarily weak compared to the magnetic effects produced by conventional currents in wires. As the experiment commenced, the magnetic needle placed near the rotating disk began to show deflection. This deflection was slight, but unmistakable. Importantly, the needle's movement corresponded directly to the motion of the charges on the disk. When the disk rotated in one direction, the needle deflected in a specific way. When the disk's rotation was reversed, the needle's deflection also reversed. This behavior was exactly what one would expect if the motion of charge itself produced a magnetic field. Such consistency across repeated trials provided compelling evidence that the effect was not due to mechanical vibrations, stray magnetic fields, or experimental error. Rowland also tested the influence of charge polarity. By reversing the sign of the electric charge on the disk, he observed that the direction of the needle's deflection reversed as well. This finding reinforced the conclusion that the magnetic effect was directly tied to the moving charges themselves, not to other aspects of the disk or its rotation. The reproducibility of these results, across variations in charge and rotational direction, was a hallmark of the experiment's rigor. Each observation aligned precisely with the theoretical prediction that moving charges produce a magnetic field, providing a clear empirical confirmation of a principle that had been largely speculative until that time. The significance of these observations extended beyond the immediate setup of the experiment. Prior to Rowland's work, magnetism had been primarily associated with electric currents in wires or the alignment of magnetic domains in materials. It was unclear whether motion alone was sufficient to produce a magnetic field. Rowland's results demonstrated unequivocally that the motion of charge itself is the fundamental source of magnetism. This insight was revolutionary, as it shifted the understanding of magnetic phenomena from being a property of certain materials or configurations to being an intrinsic consequence of charge in motion. The subtlety of the magnetic effect also highlighted the importance of experimental precision. The magnetic fields generated by the rotating charges were extremely weak, and detecting them required careful shielding and isolation from environmental influences. External magnetic fields, vibrations, and electrical interference could easily overwhelm the effect. Rowland's ability to measure these weak signals demonstrated not only his technical skill, but also the effectiveness of his experimental design. It was a testament to the meticulous planning and attention to detail that had characterized every aspect of the study. Moreover, the experiment revealed a profound symmetry in the behavior of moving charges. The magnetic field generated by the rotating disk always followed a predictable relationship with the velocity of the charges and the orientation of the rotation. This symmetry reflected the fundamental laws of electromagnetism, showing that magnetic effects are not random or contingent upon specific materials, but are governed by universal principles. Rowland's observations provided direct empirical evidence of this universality, lending support to the emerging theoretical framework developed by Maxwell and others. The implications of Rowland's observations extended into both theoretical and applied physics. The confirmation that moving charges generate magnetism reinforced Maxwell's equations and the concept of a unified electromagnetic field. It also provided a bridge to understanding magnetism at the microscopic level. If magnetic effects arise from moving charges, then the magnetic properties of materials could be explained in terms of the motion of electrons within atoms. This connection would later prove foundational for the development of atomic physics, quantum mechanics, and the study of ferromagnetism and other magnetic phenomena. In addition to its theoretical significance, Rowland's experiment had practical ramifications. Understanding that moving charges generate magnetic fields is central to the operation of electric motors, generators, and transformers. The experiment provided a conceptual foundation for designing devices in which motion and charge interact to produce controlled magnetic effects. Every application that relies on electromagnetic induction or magnetic fields owes its underlying principle, in part, to the insight provided by Rowland's observations. Rowland's experiment also exemplified the power of careful scientific reasoning. By isolating the motion of charges from other factors, he was able to test a subtle and fundamental principle directly. The clarity and reproducibility of his observations transformed a theoretical prediction into an observable fact, bridging the gap between abstract theory and empirical evidence. This approach became a model for experimental physics, demonstrating the importance of isolating variables, controlling conditions, and systematically varying parameters to confirm a hypothesis. Furthermore, the experiment had implications for the emerging understanding of electromagnetism as a unified phenomenon. By showing that motion alone produces magnetism, Rowland reinforced the idea that electricity and magnetism are deeply interconnected aspects of a single underlying interaction. This realization helped solidify the conceptual framework that would guide subsequent developments in electromagnetic theory, from the behavior of charged particles to the propagation of electromagnetic waves. In conclusion, Rowland's observations of the magnetic effects produced by a rotating charged disk provided clear, empirical confirmation of a principle that had been speculative for decades. The deflection of the magnetic needle in response to the controlled motion of charges demonstrated that magnetism arises directly from the movement of electric charge, independent of any conductor or circuit. These findings not only validated theoretical predictions, but also deepened the understanding of the fundamental relationship between electricity and magnetism. Rowland's meticulous experimentation, careful control of variables, and insightful interpretation transformed an abstract question into a concrete observation, leaving a lasting impact on both theoretical physics and practical technology. His work stands as a testament to the power of precision, creativity, and rigor in uncovering the fundamental laws of nature. The results of Henry Rowland's rotating disk experiment did more than demonstrate a subtle magnetic effect. They fundamentally established a principle that would shape the understanding of electromagnetism for generations. By showing that moving electric charges produce magnetic fields even in the absence of a conducting wire, Rowland provided the first clear, unambiguous empirical confirmation of a concept that had been theorized but not directly observed. The implications of this principle were profound, bridging the gap between abstract electromagnetic theory and measurable physical reality. At the heart of Rowland's contribution was the clarification of the mechanism underlying magnetism. Prior to his work, magnetism had often been associated with the properties of materials, such as permanent magnets, or with currents confined to wires and circuits. While Oersted's and Ampere's experiments suggested a link between electricity and magnetism, it remained uncertain whether motion itself, independent of a medium, could generate a magnetic field. Rowland's findings removed this ambiguity. By isolating moving charge from the conductor, he demonstrated that the magnetic effect arises directly from the motion of charges, not from the material carrying them. This insight revealed that magnetism is not a property of particular substances or configurations, but an intrinsic consequence of electric charge in motion. The experimental proof provided by Rowland reinforced the theoretical framework that James Clerk Maxwell had been developing. Maxwell's equations describe the behavior of electric and magnetic fields, predicting that moving charges and changing electric fields produce magnetic fields, and vice versa. While these equations had been mathematically elegant and internally consistent, empirical confirmation at a fundamental level was essential to establish their validity. Rowland's experiment served this purpose. By creating a situation in which charges moved mechanically rather than electrically through a wire, he tested the generality of Maxwell's predictions. The magnetic field observed around the rotating disk confirmed that the equations accurately described a fundamental physical principle. Moving charges inherently generate magnetism. This principle also clarified the interpretation of currents. In conventional circuits, electric currents produce magnetic fields, but the mechanism is now understood in terms of moving charges. Rowland's work established that the medium through which the charges move, whether a wire or an insulating surface, does not alter the fundamental fact that motion produces magnetism. In other words, a current is essentially organized motion of charge, and its magnetic effects are a natural consequence of this motion. This understanding transformed the study of electromagnetism from a series of empirical observations into a coherent theoretical framework grounded in clear physical principles. Rowland's experiment also had implications for the microscopic understanding of matter. If magnetism results from moving charges, then the magnetic properties of materials can be explained in terms of the motion of electrons within atoms. This insight foreshadowed the development of atomic and quantum physics, providing a conceptual bridge between macroscopic electromagnetic phenomena and the behavior of individual particles. The experiment offered a concrete demonstration that the motion of charges, whether on a rotating disk or within the electron clouds of atoms, is the fundamental source of magnetic effects. This perspective would later be essential in explaining ferromagnetism, paramagnetism, and other materials-specific magnetic phenomena. The broader significance of the experiment extends to the unification of electric and magnetic phenomena. By demonstrating that a simple motion of charges generates a magnetic field, Rowland provided evidence for the deep interconnection between electricity and magnetism. Rather than treating these forces as separate and unrelated, his findings supported the view that they are different manifestations of the same underlying interaction. This unification is at the heart of electromagnetic theory and underlies many modern technologies and scientific theories, from electromagnetic wave propagation to particle physics. The practical applications of Rowland's principle became evident as electrical technology advanced. Electric motors, generators, transformers, and countless other devices operate on the fundamental idea that moving charges create magnetic fields. By confirming that motion itself is sufficient to produce magnetism, Rowland laid the groundwork for understanding and designing these devices with confidence. Engineers and scientists could now rely on a predictable, universal principle rather than empirical approximations or materials-specific observations. The simplicity and universality of the concept made it a cornerstone of both theoretical and applied electromagnetism. Rowland's work also exemplifies the methodological rigor necessary for advancing fundamental science. Detecting the magnetic field from a rotating charged disk required careful attention to experimental design, control of variables, and systematic variation of conditions. By demonstrating the effect under multiple configurations, including reversal of rotation and charge polarity, Rowland ensured that the observed phenomenon could be reliably attributed to the motion of charges. This level of precision set a standard for experimental physics, showing how subtle and foundational principles can be revealed through carefully designed experiments. In addition, the experiment had philosophical implications for the understanding of physical forces. Prior to Rowland, there was a tendency to ascribe magnetism to mysterious material properties or hidden interactions within conductors. By isolating charge motion as the sole cause of magnetic effects, Rowland emphasized a mechanistic and universal view of nature. Forces arise from specific, identifiable physical processes, and general laws govern their behavior. This approach exemplifies a shift in physics towards seeking unifying principles that apply broadly rather than isolated rules that hold only in particular circumstances. The experiment also influenced subsequent research in electromagnetism and related fields. It provided a template for studying other subtle effects of charge motion, such as the behavior of charges in non-uniform motion, the relationship between charge acceleration and electromagnetic radiation, and the magnetic properties of complex materials. By establishing a clear and reproducible baseline, Rowland enabled later scientists to explore more intricate phenomena with confidence, knowing that the fundamental relationship between charge, motion, and magnetism was firmly established. Ultimately, Rowland's demonstration transformed a theoretical prediction into an empirical reality. It confirmed that magnetism is not contingent on specific materials or circuit configurations, but is a direct consequence of moving charges. This principle unified previously disparate observations, reinforced Maxwell's theoretical framework, and provided a foundation for both practical applications and further scientific inquiry. The experiment stands as a landmark achievement in physics, illustrating how careful experimentation can clarify fundamental laws and reshape the understanding of natural forces. Rowland's work ensured that the motion of charge would be recognized as the essential source of magnetism, a principle that continues to underpin electromagnetic theory and technology to this day. The impact of Henry Rowland's experiment extended far beyond its immediate findings, influencing both the theoretical and practical development of physics and shaping the understanding of electromagnetism for decades to come. By demonstrating that moving electric charges produce magnetic fields even without a conductor, Rowland provided empirical support for the emerging theoretical framework proposed by James Clerk Maxwell, whose equations had unified electricity and magnetism into a single, coherent field theory. This confirmation strengthened confidence in Maxwell's predictions and helped bridge the gap between abstract mathematics and observable reality, a connection essential for the advancement of modern physics. Before Rowland's work, Maxwell's equations had already indicated that electric and magnetic fields were interrelated, and that moving charges or changing electric fields could produce magnetic effects. While mathematically elegant, these equations required experimental validation beyond conventional currents in wires. Rowland's demonstration that motion alone could generate magnetism offered direct evidence for the universality of Maxwell's theory, showing that the equations accurately described nature even in situations where conduction was absent. This validation was not merely confirmatory. It reinforced the idea that electromagnetism was a fundamental, generalizable interaction rather than a collection of material-dependent phenomena. One of the most profound consequences of Rowland's findings was the conceptual unification of electricity and magnetism. By isolating the motion of charge as the essential source of magnetism, the experiment illustrated that these two forces are not separate entities, but interdependent aspects of a single phenomenon. This insight deepened the theoretical understanding of electromagnetic fields, providing a tangible, experimental demonstration of a principle that had previously been largely abstract. The unification of electricity and magnetism, confirmed through Rowland's work, set the stage for later breakthroughs in physics, including the recognition of light as an electromagnetic wave and the eventual development of quantum electrodynamics. Beyond theoretical validation, Rowland's experiment influenced the study of materials and microscopic phenomena. If moving charges generate magnetism, then the magnetic properties of substances can be explained by the motion of electrons at the atomic level. This principle became foundational for atomic physics and later quantum mechanics. Rowland's work provided empirical grounding for hypotheses that had suggested magnetism within materials arises from microscopic currents, offering a clear link between observable macroscopic effects and the behavior of subatomic particles. In this sense, the experiment anticipated later discoveries about the electron, atomic structure, and the magnetic behavior of ferromagnetic and paramagnetic materials. The technological implications of Rowland's experiment were equally profound. Modern electrical devices, from generators and motors to transformers and magnetic storage systems, operate on the principle that moving charges produce magnetic fields. By confirming this relationship experimentally, Rowland provided a reliable foundation for designing and optimizing electromagnetic devices. Engineers and inventors could now apply the principle with confidence, knowing that the magnetic effect depended solely on charge motion and was independent of specific materials or circuit arrangements. This universality allowed for greater flexibility in device design and facilitated rapid technological advancement during the late 19th and 20th centuries. Rowland's experiment also exemplified the evolving nature of experimental physics in the 19th century. It combined conceptual clarity with technical precision, reflecting a shift toward controlled, quantitative studies that isolated specific variables. This approach contrasted with earlier, more qualitative investigations and demonstrated the power of careful experimental design to reveal subtle physical principles. The experiment required not only an understanding of theoretical predictions, but also meticulous attention to practical details: the uniform distribution of charge, the stability of rotational motion, and the sensitivity of magnetic detection instruments. By successfully controlling these factors, Rowland was able to detect extremely weak magnetic effects and provide unequivocal evidence for a fundamental law of nature. Furthermore, the experiment served as a model for subsequent scientific inquiry. It showed that profound physical truths could be revealed through relatively simple setups if the experiment was designed thoughtfully and executed with precision. The principle that moving charges produce magnetism, demonstrated so clearly by Rowland, inspired further investigations into electromagnetic phenomena, including the study of induced currents, behavior of charged particles in magnetic fields, and the interactions of electromagnetic waves with matter. Rowland's work established a standard for linking theoretical predictions with empirical observations, emphasizing the importance of reproducibility, control, and systematic variation in experimental science. The broader influence of Rowland's findings extended into the conceptual foundations of physics. By clarifying the relationship between motion and magnetism, he helped establish a mechanistic and universal view of physical forces, in which effects can be traced to identifiable causes. This perspective was essential for the development of classical field theory, and later for the understanding of interactions at the quantum level. The clarity provided by Rowland's experiment reinforced the idea that electromagnetic phenomena could be explained through consistent principles, rather than being attributed to mysterious or material-specific properties. Rowland's work also played a key role in bridging the gap between theory and application. While Maxwell's equations provided a theoretical description of electromagnetic fields, the practical demonstration that moving charges generate magnetism enabled the design of devices that could exploit this principle. Electric generators, for example, convert mechanical motion into electrical energy through the interaction of moving charges and magnetic fields. Motors operate on similar principles in reverse. Without experimental confirmation of the underlying relationship, such applications would have relied on empirical approximations rather than a clear understanding of the physical mechanisms involved. Rowland's experiment provided that essential confirmation. In addition, the experiment reinforced the predictive power of theoretical physics. By validating the prediction that moving charges produce magnetic fields independent of a conductor, Rowland demonstrated that theoretical equations could reliably describe natural phenomena even in novel circumstances. This confidence in theory-driven experimentation paved the way for future advances, including the study of electromagnetic radiation, the exploration of atomic-scale phenomena, and the development of modern electrical and communication technologies. In summary, the impact of Rowland's experiment was wide-ranging and multifaceted. It confirmed a fundamental principle of electromagnetism, strengthened Maxwell's theoretical framework, and clarified the nature of magnetism as a direct consequence of moving charges. The work influenced the study of materials, laid the foundation for technological innovation, and exemplified the power of precise experimental design in revealing subtle physical laws. By translating a theoretical prediction into an observable effect, Rowland connected abstract concepts with tangible reality, providing a model for scientific investigation that continues to inform both theoretical and applied physics today. His experiment stands as a landmark achievement, demonstrating how careful observation, rigorous methodology, and conceptual insight can transform understanding and shape the future of science. The culmination of Henry Rowland's work on the relationship between moving electric charges and magnetism marked a defining moment in the history of physics. By demonstrating empirically that motion alone generates a magnetic field, Rowland not only confirmed theoretical predictions, but also laid the foundation for a wide array of subsequent scientific and technological advances. The seventh and final implication of his experiment is best understood in terms of its enduring influence on both the conceptual framework of electromagnetism and the broader trajectory of modern physics. Rowland's work provided an unambiguous experimental validation of a principle that had long been hypothesized but never conclusively observed, that magnetism is fundamentally tied to the motion of electric charge. This insight clarified a major conceptual ambiguity in the field. Before Rowland's experiment, magnetic effects were often attributed to currents confined to wires or to materials' specific properties. Even after Maxwell's theoretical unification of electricity and magnetism, there remained a question of whether the presence of a conducting medium was essential for producing a magnetic field. Rowland's rotating charged disk eliminated this uncertainty. By mechanically moving charges without a wire, he proved that magnetism arises intrinsically from charge motion, independent of material or circuitry. This clarity allowed physicists to approach electromagnetism with a deeper understanding, setting the stage for more advanced explorations of the phenomenon. The implications of this work extended into atomic and subatomic physics. If macroscopic magnetic fields arise from moving charges, it follows that the magnetic properties of materials can be explained by the behavior of electrons within atoms. Rowland's demonstration provided a direct macroscopic analog to the microscopic currents proposed by Ampere and others, reinforcing the idea that atomic and subatomic motions are responsible for observable magnetic effects. This perspective became crucial for the development of quantum mechanics and the study of electron spin, orbital motion, and magnetic interactions within matter. In essence, Rowland's experiment bridged the gap between macroscopic observations and microscopic theory, showing that fundamental physical principles operate consistently across scales. Moreover, the experiment underscored the predictive power of theoretical physics. Maxwell's equations had suggested that moving charges generate magnetic fields, yet experimental confirmation under varied conditions was essential to establish the universality of the principle. Rowland's meticulous measurements demonstrated that theory could reliably predict the outcomes of carefully designed experiments, reinforcing confidence in the equations as a model of physical reality. This empirical confirmation provided a template for the interplay between theory and experiment that defines modern physics. Hypotheses are formulated mathematically, then subjected to precise testing to validate their applicability in the real world. The technological ramifications of Rowland's work cannot be overstated. By demonstrating the fundamental relationship between charge motion and magnetism, he laid the groundwork for the design and operation of countless devices. Electric motors, generators, transformers, and other electromagnetic devices operate on the principle that moving charges produce magnetic fields. Understanding this principle allowed engineers to predict and control magnetic effects with precision, enabling the development of efficient energy conversion systems and advanced communication technologies. Without the experimental clarity provided by Rowland, the application of electromagnetic principles would have remained largely empirical, lacking the theoretical confidence necessary for rapid technological progress. Rowland's experiment also exemplified the evolving methodology of physics during the 19th century. The study combined conceptual insight with rigorous experimental design, reflecting a shift from purely observational science to a more systematic, quantitative approach. By isolating variables, controlling environmental conditions, and carefully measuring subtle effects, Rowland demonstrated that even weak phenomena could be reliably observed and analyzed. This emphasis on precision and reproducibility influenced future generations of physicists, establishing standards for experimental methodology that persist to this day. Another enduring impact of the work lies in its reinforcement of the unity of physical laws. By showing that moving charges invariably produce magnetic fields, Rowland provided evidence for the universality of electromagnetic interactions. This insight helped solidify the notion that seemingly distinct phenomena, electric currents, moving charges, and magnetic fields, are manifestations of a single underlying interaction. Such unification is a hallmark of modern physics, influencing not only electromagnetism but also the development of field theory, the study of fundamental forces, and the search for a unified description of nature. Rowland's careful experimental approach also highlighted the importance of isolating fundamental principles from secondary effects. By eliminating the conductor from the experimental setup, he removed potential confounding factors and demonstrated that the observed magnetic effect was intrinsic to the motion of charges. This methodological rigor serves as a model for scientific investigation, illustrating how isolating variables and minimizing external influences can lead to clear and reproducible insights. The approach reinforced the broader scientific philosophy that observable phenomena must be linked directly to well-defined physical causes, a principle that underpins modern experimental physics. The clarity and reproducibility of Rowland's findings also had implications for education and communication within the scientific community. By providing a simple yet elegant demonstration of the principle, his experiment could be understood, replicated, and built upon by other researchers. This accessibility ensured that the insight that moving charges inherently generate magnetic fields became widely accepted and incorporated into the foundational knowledge of physics. In this way, Rowland's work not only advanced scientific understanding, but also shaped the pedagogical and conceptual frameworks through which electromagnetism has been taught for over a century. Finally, Rowland's experiment serves as a historical example of how careful empirical work can resolve long-standing theoretical ambiguities. By transforming an abstract hypothesis into observable, measurable reality, he demonstrated the power of experimental physics to clarify fundamental principles. The experiment reinforced the idea that scientific knowledge advances through a combination of theoretical insight, precise measurement, and rigorous validation. This model has guided countless subsequent discoveries in physics, from the behavior of subatomic particles to the development of modern technologies based on electromagnetic principles. In conclusion, the seventh and final significance of Rowland's work lies in its enduring influence on both the conceptual and practical domains of physics. By proving that moving charges generate magnetic fields independent of conductors, he provided definitive empirical confirmation of a foundational principle, reinforced the predictive power of theoretical models, and established a methodological benchmark for experimental precision. The experiment bridged macroscopic and microscopic perspectives, informed technological innovation, and exemplified the unity of electromagnetic phenomena. Its legacy continues to shape the study and application of physics, demonstrating how a carefully conceived and executed experiment can illuminate the fundamental workings of nature and guide the trajectory of scientific progress for generations.